He's one of my heroes because he gives me faith in humanity, which I desperately need at the present time. Because he began life as a lawyer and became an astronomer. So there's hope. And, but he did many, many things. One of the first things he did, which is actually somewhat peripheral to what I want to talk about, but probably worth mentioning, is well, up to that point with large telescopes, in 1925 he was using the Mount Wilson telescope, newly built. And up to that point, if you looked at our galaxy with the largest telescopes then available, you'd see stars, and then you saw these little fuzzy things, which were called nebulae, which is Greek for fuzzy thing. And there was big debate about what they were. And what Hubble was able to show, in fact, in 1925 with the Mount Wilson telescope, is that actually he was able to distinguish stars in them and discover, in fact, that there were other island universes, other galaxies. Until that point, until 1925, we knew of one galaxy in the entire universe. That was it. Our universe was the Milky Way galaxy. And we now know that there are over 400 billion galaxies in the observable universe. So in a single human lifetime, in 87 years, we've gone from 1 to 400 billion. We're like the early map makers. It's not surprising that we're surprised, in fact, and our picture of the universe is changing dramatically, and it's those changes I want to describe to you today. Now, the discovery of the expanding universe is important enough I want to describe a little bit. So, what did he see? Well, he saw this. We're here, these are galaxies, not sperm. And so, if we're on our galaxy here, we look out, we see all the galaxies on average, and what Hubble saw, all of the galaxies on average were moving away from us with a certain velocity, and those that were twice as far away were moving away from us with twice the velocity. Those that were 3 times far away were moving away from us 3 times the velocity. So what does this tell you? It's obvious what it tells you. We are the center of the universe. That's what it looks like. It certainly seems that way. But as many of my friends remind me on a daily basis, that's not true. In fact, what it really means is the universe is expanding. But the problem is we're stuck in our galaxy. We're stuck in our universe. Well, most of us are. The Republican candidates aren't. That's an easy laugh. But in any case, so if we want to see what's happening, we've got to get out of our universe, and that's hard. But I can do it with the universe I can create on the computer, where I want to get outside the box. So I make this universe, a 2-dimensional universe. It's easy to draw. We're outside of it, and this is a region of it. And I put galaxies at nice uniform distances apart at time t1, and at some time t2, you can see they're a lot further apart from each other. The region has expanded. So if you were standing outside that universe, you would in fact see that it was expanding. But what would you see if you lived in that universe? Well, let's pick a galaxy, any galaxy. So to see what it looks like in that universe, I'm going to superimpose this image on top of this one, placing this on top of this. Okay? So what do we see? We see exactly what Hubble saw. Every galaxy is moving away from you, and those that are twice as far away have moved twice the distance at the same time. Those that are 3 times as far away have moved 3 times the distance, and so on. And it doesn't matter what galaxy you pick. You see the same thing from every galaxy. So depending upon your mood, either every place is the center of the universe, or no place is the center of the universe. It doesn't matter. It really doesn't matter. What it really matters is that the universe is expanding. And what Hubble discovered is the universe is expanding, and that was profoundly important. It changed everything, because it meant our universe had a beginning, which had profound implications for science, but it also had profound implications for theology and everything else. It meant our universe had a beginning. We now know that beginning was 13.72 billion years ago, except in Arkansas and a few other places. Maybe Alberta, I don't know. But it is 13.72 billion years old, and that is amazing, that we even know that to 4 significant digits. I never would have thought in my lifetime we would know that. But I want to tell you how we know it, because, okay, this is physics, not philosophy. So if you have this discovery, you're measuring things. You're measuring the velocity of objects as a function of their distance. Objects that are further away are moving away from us faster. So how can you measure this? Well, you have to measure velocity and distance. So how do you measure velocity? That's the easy part, it turns out. And these 2 cowboys know how to do it. One of them is talking to the other as they look at that train on the prairie. And one says to the other, I love hearing that lonesome wail of the train whistle as the magnitude and the frequency of the wave changes through the Doppler effect. Because what they're talking about is the famous fact that when a train is coming towards you, the train whistle gets higher. When the train is moving away from you, the train whistle gets lower because, in fact, the waves stretch out behind the train. They scrunch up in front of the train. The frequency goes up in front, gets lower behind. For very different reasons, it turns out the same thing happens to light. So for objects that are moving away from us, the light from those objects gets stretched out to longer wavelengths. And the red end of the spectrum is the longest wavelength end of the spectrum, so we say they're redshifted. The ones moving towards us are blue shifted. And what Hubble discovered is that the objects that are systematically further away from us are systematically more redshifted. So that's easy. Measure the redshift, you know the velocity. But how did he know which objects were systematically further away from us? That's the hard part. That's always been the hard part in cosmology, because those objects are far away. We don't have tape measures that are that long. So we've got to think of some way to measure distance without a tape measure. And of course we use the laws of physics. And I could measure the distance to the back of the room by turning off all these lights except for one, and say a 100-watt light bulb. And if some of you are as old as I am here, you remember cameras that had light meters. And if you used to have a camera that had a light meter, if I knew there was 100 watts coming from that light, and my camera, I detected 1 watt, I know that the light spreads out in a certain way, in a well-defined way, and I can work backwards and figure out how far away that light bulb is. So if the universe were populated by 100-watt light bulbs, we'd be fine. But it isn't, so we have to look for something like a 100-watt light bulb, something we call a standard candle, something whose intrinsic brightness we understand. And then we look at it through a telescope and see how bright it looks. And if it's fainter, it's further away. If it's brighter, it's closer up. So we need standard candles, and that's the hard part. And in fact, it was the hard part when Mr. Hubble was doing his data analysis. This was in 1929. This is his original data for 1929. Velocity is a function of distance. And one of the reasons he was such a great scientist, in fact, was he knew to draw a straight line through that data set. It's not obvious that's the right thing to do. When he did, he got the rate at which the universe was expanding, and one of the wonderful things he did for us was he got it wrong by a factor of 10. It was wonderful because astrophysicists have tried to emulate that ever since with their work, in many ways. But more importantly, it actually demonstrated that scientists can sometimes change their minds. Because if you work it out, when the universe he discovered the universe was expanding about 10 times faster than it actually is. And if that were the case, if you know how fast it's expanding, you can work backwards and figure out how old it is. And if the universe was expanding as fast as Mr. Hubble estimated, the universe would be about 1.5 billion years old. But even in 1929, except in Arkansas and a few other places, we knew the Earth was 4.5 billion years old. We knew it was more than 1.5 billion years old. And it was a real embarrassment to have the Earth be older than the universe. And so that could have been a real problem for the whole picture. But happily, of course, it wasn't a problem, because we now understand the actual expansion rate is almost a factor of 10 lower, and the universe is not 1.5 billion years old, but 13.72 billion years old. Now, the reason we can do that better is, one of the reasons is we have better standard candles. Hubble didn't have them, and this is one of the best standard candles we've ever been able to get. In fact, it is the best. This is a galaxy long, long ago, far, far away. Not actually that far away. It's only 50 million light years away. So it takes 50 million years for the light from these stars to get to the camera that took the picture. And it's a spiral galaxy, much like our own. When you've seen one, you've seen them all, more or less. And what you see here is a very bright star. Now, the interesting thing is, this galaxy contains about 100 billion stars. And the center of the galaxy contains about 10 billion stars. And this star is shining as brightly as the whole center of the galaxy. Now, how can that be? Well, the first thing to assume is that, in fact, it's a star in our galaxy that got in the way of the picture, which is a reasonable assumption. But it's not true. It actually is a star at the edge of that galaxy. And it is shining with a brightness of 10 billion stars, because it is a star that has just exploded. A supernova. The brightest cosmic fireworks in the universe. When stars explode, they briefly shine with a brightness of 10 billion stars for a period of a month or so. Now, fortunately for us, stars don't explode that often. About once per 100 years per galaxy. But fortunately for us, they explode. Because, in fact, if they didn't, you wouldn't be here. Because in the Big Bang, the only elements that were created were hydrogen, which is protons, and helium and a little bit of lithium. But the really, well, for some of you, lithium may be important, but for the rest of you, the really important stuff is carbon, nitrogen, oxygen, iron, all that stuff that makes us up. None of that is created in the Big Bang. It's created in the fiery nuclear furnaces in the cores of stars. And the only way it could get into your body is if the stars were kind enough to explode. And in fact, over the last 12 billion years or so, 200 million stars have exploded in our galaxy. And the atoms in every atom in your body has been through that incredible, one of the most violent explosions in the universe. You are indeed stardust. You're all star children. It is, in fact, the most poetic thing I know about physics. And the atoms in your left hand may have come from a different star than your right hand. But every one of them has perhaps been through not one, but maybe many stellar explosions. It is truly amazing to think how you are connected to the cosmos in ways, as I say, that you never would have imagined. But so much for that. We want to use these objects, these stellar explosions, type 1a supernova, this one's called, to measure the expansion rate of the universe, but they only explode once per 100 years per galaxy. So how are we going to do that? Well, it's quite simple. We can assign a graduate student to each galaxy. 100 years is about the right time for a PhD. And graduate students are cheap. If they die, just get a new one. Well, we don't have to do that. We don't have to do that because the other amazing thing about the universe, which people don't realize, is it's big and it's old, and therefore rare events happen all the time. If you go out in the night sky tonight and hold your hand up and hold a dime-sized hole in your hand, you still have dimes here, right? Yeah. Okay. In a dark spot in the sky, where there are no stars, with one of the largest telescopes we have in the world right now, and looked in that region, you would see about 100,000 galaxies. And if you work it out once per 100 years per galaxy, you have 100,000 galaxies on a given night, you'll expect to see a few stars explode. And astronomers do that. They apply for telescope time, they say we're going to see some stars explode tonight, and we can study them as a result. And so we can watch them before they explode and afterwards. And here's a movie of a star exploding in this particular galaxy. We can see its brightness, it'll repeat. We can see its colors, which tells us it's a certain type of supernova, a type 1a supernova, which, for reasons I can't go into, is a wonderful standard candle. In fact, people using this standard candle have been able to measure the expansion rate of the universe, and it's so important that the people using this standard candle won the Nobel Prize in Physics last year for their work, as I'll describe. Now, in fact, using these standard candles, we can get a much better Hubble plot than we used to. This, of course, is developed after the important discovery that in a log plot, everything is a straight line. But beyond that guide for the eye, we actually can measure the expansion rate of the universe, now not to a factor of 10, but instead 10% accuracy. In fact, better than 10%. So we know how fast the universe is expanding. And that is one piece of the puzzle. Because what we really want to know, I remind you, is how will the universe end. In fact, the reason I got into physics, into cosmology, I'm a particle physicist by training, was that I thought I could answer that question. I could be the first person to know how the universe would end. It seemed like a good idea at the time. And that's why I got interested in this business. And I told you that Einstein says that matter curves space, matter and energy. And that means it turns out that our universe can exist, our three-dimensional universe, can exist in one of three types of geometries. Now, I can't draw those geometries for you because I can't draw three-dimensional curved surfaces, because we live in three dimensions. But I can draw curved two-dimensional surfaces as a guide to the eye, but that's all they are. But our universe can be so-called open, closed, or flat. And you can see the two-dimensional open, closed, and flat surfaces. You have to imagine it in three dimensions, and it's hard to picture. You can operationally describe, say, a closed universe. In a closed universe, if you look far enough in that direction, you see the back of your head. Okay, the light will go right around the universe. And all that sounds nice, but what's really important is in a matter-dominated universe, in a closed universe, it will expand and then stop and recollapse in a big crunch, the reverse of the Big Bang. An open universe will go on expanding forever, and a flat universe is the boundary between the two. Will go on expanding, slowing down, and never quite stopping. And the question is, which universe do we live in? And if we want to answer that, it's quite simple. We just have to weigh the universe. So, there you go. And to weigh the universe, well, you stand on the shoulders of giants. Now, in fact, it turns out that I wrote a whole book about weighing the universe once, but it turns out we've done it. And I want to tell you how we've done it. I want to take you back in history a little bit. For the students especially, because I want to remind you of a kindler, gentler time. When to be a scientist was a little bit nicer. In 1936, in the science journal Science, an article appeared entitled, "Lens-like action of a star by the deviation of light in a gravitational field." And here's how the article began. This is Science magazine. "Some time ago, R.W. Mandel paid me a little visit and asked me to publish the results of a little calculation which I made at his request. This note complies with his wish." I try that nowadays and see what happens. Now, it turned out the author had credentials. His name was Albert Einstein, so it was easier for him to get published. But what he published was the result of a calculation that he thought was unimportant. That's one of the bases of general relativity. He knew that space curved and light traveled in curved trajectories around massive objects. And he realized that if you had a massive enough object and you had a light source behind the massive object, the light rays could go around it and bend around and come back and converge and be magnified like my glasses do for nearby objects. Or if you had a cut glass goblet, if you look through that, I'd see many versions of you in this room. And Einstein realized that space could do that. It could act like a lens. But he said the effect is so small we'll never measure it. He thought it was so unimportant he wasn't going to publish it until Mr. Mandel convinced him to. And in fact, it was so this is the calculation he did in 1936. This is his notebook. And it was so unimportant that he actually forgot that he'd done it in 1912, exactly the same calculation if you go back. And it's kind of amusing if you see what he wrote the editor right afterwards. He said, "Let me also thank you for the cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." So that's how science is done, ladies and gentlemen. Anyway, he didn't think it was important, but it is, because it's the way we weigh the universe. Because Einstein didn't know about galaxies, he just knew about stars. And here is an image of the very phenomena which he said we'd never see. This is a Hubble Space Telescope picture of a cluster of galaxies. Every point in this picture is a galaxy, not a star. And every one of these galaxies contains perhaps 100 billion stars. This cluster is 5 billion light years away from us. So it takes the light from this cluster 5 billion years to get to us. The light was emitted before our Earth and our Sun ever formed. In fact, nowadays, most of these stars may not exist. And maybe the civilizations around those stars, which may have developed 5 billion years ago, don't exist. In those hundreds and hundreds of billions of stars. Again, I find inspiration when I see pictures like this. But the thing about clusters is they're the biggest bound objects in the universe. Almost all galaxies are in clusters. We're in one. And if you could weigh the clusters, since anything that can fall into anything will fall into a cluster, if you could weigh the clusters, you weigh the universe. And we've been able to weigh the clusters with gravitational lensing. You don't have to be a rocket scientist to see that there's weird things in this picture. Blue galaxies. And what these are multiple images of a single galaxy located 5 billion light years behind that cluster. And the light from that galaxy is curved and magnified, makes it bigger, but also split into many images. All of these images are of the same galaxy, demonstrating that space is curved and relativity works. But more importantly, we know that relativity works, so we can work backwards. We can say, from this image, how much mass would you have to have in that picture to make that image, and where would it be distributed? It's a complicated thing called a mathematical inversion, but you can do it. When you do it, you come up with this picture here. This is the spikes. This is where the mass is in this image. The spikes are where the galaxies are. But you notice that most of the mass, this big mountain of mass, is where the galaxies aren't. There's 40 times more mass in that picture than can be accounted for by what you can see. And physicists who have such incredible creative imaginations call this stuff dark matter, because it doesn't shine. And what we discovered is not just in this object, but in all objects, most of the mass of the universe, 40 times as much mass of the universe, doesn't shine as shines. And in fact, there's so much of it that we are now virtually certain that it can't be made of the same stuff as you and me. It can't be made of protons and neutrons, because we know how many protons and neutrons are in the universe, it turns out. And there's 10 times too much of that stuff to be accounted for by all the protons and neutrons that we know are in the universe. So we're pretty certain it's a new type of elementary particle. Something doesn't exist here on Earth. But that makes it exciting because that means it's not just out there. It's in this room. It's going right through your bodies as you nod off during this lecture. Okay? And that means most of it's going right through the Earth. And we can look for it not just by building telescopes, but by building experiments here on Earth, deep underground. Because in fact, we're being bombarded by cosmic rays every day, and you want to screen them out. They get stopped by the rock at the top of the Earth. But if you build a deep mine and put an experiment down there, the cosmic rays will get screened, but these dark matter particles, since we think they interact so weakly, will go right through. And most of the time, they go right through the Earth without knowing what's there. But every now and then, they might bounce off a nucleus of an atom in a detector, and we're building detectors around the world to look for that dark matter. And in fact, it's even more exciting because it turns out the other place to look for it is not the dark matter that came from the beginning of time, as this dark matter does. We think it was created in the earliest moments of the Big Bang. But if we could recreate those earliest moments, maybe we could recreate that dark matter, and we look for a place where we recreate the earliest moments of the Big Bang. There's such a place on Earth right now. It's outside Geneva, Switzerland, making neutrinos that don't go faster than light, and, in case you hadn't heard. But they may also, over a brief, very small scale, they recreate conditions of the very early universe, and maybe they'll create the new elementary particles themselves and we'll detect them. So it's a race between those people who are building those underground detectors and the people of Large Hadron Collider to find out what this dark matter is. But we don't need to know what it is, because at least for this purpose, because we know how much of it there is. We weigh this system, and we weigh all systems like it, and we have finally weighed the universe, and we have the answer. And drum roll. There it is. I hear a gasp. Excitement. Well, physicists, whenever they get an important quantity, they give it a Greek letter to make themselves look scholarly. So we call it omega. And omega is the ratio of the actual amount of stuff in the universe divided by the amount you'd need to make a flat universe. So if omega is less than 1, the universe is open. If it's greater than 1, the universe is closed. And if it's exactly equal to 1, the universe is flat. And what we've now discovered with unimpeachable accuracy is that there's only 30% of the amount of stuff in the universe needed to make it flat. We live in an open universe, case closed. But there's a problem. We theorists knew the answer. We always know the answer. We're not often right, but we always know the answer. We knew that the universe was flat. Why? Because a flat universe is the only mathematically beautiful universe. Actually, for reasons I'll describe in a little bit. And here these damn observers were getting the wrong answer, which they always do anyway. But of course, this is a very indirect way of determining the geometry of the universe, because you have to measure the expansion rate, and you plug in the amount of matter, and you compare the two things using Einstein's equations. Wouldn't it be better to measure the curvature of the universe directly? And what is remarkable is in the last decade or so, we've been able to do that. I want to show you how. I never would have thought it would have been possible. Actually, it turned out I wrote a paper about it 20 years ago, but I forgot. How can you measure the geometry of the universe directly? Well, very simple. How would you measure the curvature of the Earth if you couldn't go around it or couldn't go into outside space and look at it? Very simple. You draw a triangle, and you ask a European high school student, what's the sum of the angles in the triangle? And maybe a Canadian high school student. They say 180 degrees. Fine, but you say, well, that's because you learned your geometry from Euclid. On a curved surface, I can draw a different kind of triangle. I can go around the equator, and I can draw a line along the equator, make a 90-degree angle, go up to the North Pole, make a 90-degree angle, go back to the equator. And now I have a triangle with 3 right angles. 3 times 90 is 270. That's not 180. That tells me I have a curved surface. So to tell that the Earth is curved, you just would have to draw a big enough triangle, and you would see that that didn't add up to 180, some of the angles. It's very simple. And it turns out that that intuition, or that mathematical fact, is absolutely true, not just for curved 2-dimensional surfaces, but for curved 3-dimensional spaces. So in our universe, if we could draw a triangle that was big enough, and measure it, and measure the angles, we can measure if our universe is curved. And that's what we've been able to do. We've been able to find a big enough triangle, and we get it from one of the most important observations in cosmology, the cosmic microwave background radiation. The afterglow of the Big Bang. Discovered in New Jersey, of all places, by 2 people who didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. No, you don't. You just have to discover something, and you did.